Nuclear reaction in stars. Simply put, a star is a massive cosmic factory. Deep within its intensely hot core, immense gravity force led atoms to combine into heavier elements through a process called nuclear fusion. This very process releases a staggering amount of energy, providing the outward pressure needed to stop the star from collapsing under its own gravity. In this presentation, we will dive deeper into this cycle, starting from basic hydrogen fusion via the proton-proton chain, or we call PP chain, in medium-sized star like our Sun, all the way to the advanced burning of heavier elements like helium, carbon, and silicon in massive stars. Let's explore how this nuclear reaction do not just power the stars, but also lay down the chemical foundation of our entire universe.
Mass energy equivalence states that the mass of an object is measure of its energy content and conversely energy possesses mass. The relationship is mathematically expressed as E equal to mc square, where E is energy in joule, m is a mass in kilogram, and c is the speed of light in a vacuum, 3 times 10 power of 8 meter per square. This implies that even a small amount of mass corresponds to a 3 meters amount of energy due to the large value of c squared. The equation applies to objects at rest and can be extended to moving objects using relativistic mass and energy. Next is why equation E equal to mc squared important. It shows mass can convert into energy and vice versa. Even a tiny amount of mass can produce a huge amount of energy because c squared is large. This principle explains the energy in stars and nuclear reactions. For example, 1 gram mass equal to 9.0 times 10 power of 3 joule. Next is, what is the proton-proton chain? The proton-proton chain is a series of nuclear fusion reactions in stars that convert hydrogen into helium, releasing energy in the form of gamma ray, neutration, and kinetic energy. In a proton-proton chain, 4 hydrogen nuclear protons are combined to form one helium nucleus. First, 2 hydrogen nuclei combine to form a hydrogen power of 2 nuclei with the emission of positive electron, then rapidly captures another proton to form a helium with power of 3 nucleus while emitting a gamma ray. And the overall 4 hydrogen atoms combine to produce one helium atom and release energy.
Binding energy is the energy required to separate a nucleus into individual protons and neutrons. This energy exists because nucleons are held together by the strong nuclear force. A nucleus with higher binding energy per nucleon is more stable. In nuclear fusion, light nuclei combine to form a heavier nucleus with greater stability. During this process, a small amount of mass is lost, called mass defect. According to Einstein's equation, this lost mass is converted into a large amount of energy. This explains why fusion can produce enormous energy, such as in the Sun. The binding energy per nucleon increases as nuclei become larger, but only up to iron, which is Fe56. Iron is one of the most stable elements because it has the highest binding energy per nucleon. This creates the iron limit in nuclear fusion. Fusion of light elements such as hydrogen and helium release energy because the product becomes more stable. However, when elements heavier than iron are fused, energy must be absorbed instead of released. This theory is important in astrophysics because it explains why stars can produce energy only until iron is formed in their core. After reaching the iron limit, fusion can no longer support the star effectively.
Now, I will discuss the application of nuclear reactions in stars through the ITER project. ITER, which stands for International Thermonuclear Experimental Reactor, is currently the world's largest nuclear fusion experiment. The main goal of this project is to determine whether fusion can become a practical and sustainable energy source for humans in the future. The reason ITER is closely related to our topic is that it is based on the same principle that power stars. In stars like the Sun, hydrogen nuclei fuse together and release enormous amounts of energy. Scientists are trying to recreate this process on Earth. However, instead of using gravity like stars do, ITER uses extremely strong magnetic fields to confine the hot plasma and maintain the fusion reaction. This research is important because fusion has the potential to provide a clean and abundant source of energy. Unlike fossil fuels, fusion does not produce greenhouse gases during operation, and it requires only a small amount of fuel to generate a large amount of energy. Therefore, if ITER is successful, it could play a major role in meeting future global energy demands while reducing environmental impact. In conclusion, ITER demonstrates how our understandings of nuclear reactions in stars can be applied to develop advanced energy technologies here on Earth.
Okay, so for this slide, I'm going to talk about some career path related to nuclear reaction in stars. First, we have astrophysicists. Astrophysicists are study about how stars produce energy through nuclear fusion. They also research nuclear synthesis. They are work in university and space agency. Then, nuclear physicists. Nuclear physicists are study about nuclear reaction found in stars. They apply knowledge in fusion energy technology and work in lab or energy sector. Next, astronomer. They observe star and star behavior, study life cycle from birth to death, and work in observatories or space agency. We also have space scientists or researchers who study different space phenomena and can be involved in real missions or simulation with agencies like NASA or ESA. Lastly, scientist educator or lecturer. They are play an important role by teaching this concept and inspiring future scientists. For self-development, there are three key aspects to focus on. First, in terms of knowledge and skill, it is important to strengthen foundational knowledge in physics and mathematics. At the same time, develop programming and data analysis skills, as well as critical thinking. It's help in solving complex scientific problems. That's for personal growth. Staying curious about the universe and practicing independent learning through reading and research are essential. In addition, strong communication and teamwork skills are important for future collaboration. Finally, for future preparation, joining STEM competition can help sharpen solving problem abilities, gaining hands-on research experience, and planning ahead for a degree in physics or related scientific field are also important steps.
In conclusion, the life cycle of a star is fundamentally a beautifully ordered series of temperature-dependent nuclear reactions. A star begins its life by burning hydrogen as it ages and gets hotter. It moves on to fuse heavier elements like carbon, neon, oxygen, and silicon. Each of these stages yields new elements while generating the critical energy needed to keep the star stable. However, this delicate energy balance comes to a permanent halt on an iron 156 core is formed. At this unit threshold, fusion shifts from a process that releases energy to one that absorbs it. Deprived of its energy source, the star instantly collapses, triggering a catastrophic supernova explosion. Ultimately, this stellar nuclear reaction serves as the primary engine for cosmic nucleosynthesis, the process that transforms primordial hydrogen into the diverse, complex elements we see today. Without these reactions, the carbon in our DNA or the iron in our body simply will not exist. Thank you.